Welcome back. Welcome back to the course Geology and Soil Mechanics. So, as we decided in the last lecture that we will be solving few problems on permeability in soil. So, the first problem that is the problem number 9. It says that a falling head permeability test was carried out on a 15 centimeter long sample of silty clay. The diameter of the sample and the standpipe were 9.8 centimeter and 0.75 centimeter respectively. The water level in the standpipe was observed to fall from 60 centimeter to 45 centimeter in 12 minutes. Determine the following. First one, the coefficient of permeability of the soil, height of water level in the standpipe after another 20 minutes, and time required for the water level to drop to 10 centimeter. So, this problem is basically based on the theory which we have covered in falling head permeability laboratory test. So, let us solve this problem. So, we will go to the problem directly. So, this is your problem 9. Now, for a falling head permeability test, we have, so this we know from our theory whatever we have covered in the lecture, that is K, that is the coefficient of permeability or the hydraulic conductivity, that is expressed as A into L. What is A? A is the area, cross sectional area of the standpipe, L is the sample length, divided by capital A into T, where capital A is the cross sectional area of the soil sample, soil specimen, and T is the time, into log base E H1 by H2. That is the, whereas H1 is the initial head and the H2 is the final head, and that basically this expression is known to us, and we have derived this expression and we have seen how we have got this expression. So, there is no issue, we will not further discuss about this equation. So, here in this problem, your A, that is the cross sectional area of the standpipe, can be obtained as pi by 4 into 0.75 whole square, where 0.75 centimeter is nothing but the diameter of the standpipe as given in the problem. So, that comes as, so I will keep that thing as it is. So, because I do not need to calculate this thing, you will see that why. Well, so capital A, that is the cross sectional area of the soil specimen, that comes as 9.8 whole square, where 9.8 centimeter is nothing but the diameter of the soil specimen. Okay. Now, what is the L? Length of the soil specimen that is given in the problem, that is 15 centimeter, and T, that is given in 12 minutes, right, because it takes 12 minutes from 60 centimeter head to 45 centimeter head. So, that comes as 720 seconds, okay, in terms of second. H1, that is the initial head, okay, from where you are starting or you are initiating the experiment. So, that is given as 60 centimeter, and what is the final head you have observed after 12 minutes, that is 45 centimeter. So, these are the parameters are given in the problem. So, now we will calculate K as pi by 4 into 0.75 whole square, that gives us small a, into 15, that is L, divided by capital A, pi by 4 into 9.8 square into 720 ln 60 by 45. So, we did not calculate the area because we will take the advantage over here. So, they will get cancelled. So, ultimately I will get 3.51 into 10 to the power minus 5 centimeter per second. So, this is your coefficient of permeability or the Hartley conductivity, right. So, as you have seen, so basically I mean this expression was known to you. Now, basically whatever parameters are given in the problem, based on that you have calculated all the things and your permeability is coming 3.51 10 to the power minus 5, and that will be remaining same for the rest of the test. I mean whatever you do the test, because permeability will not be changing as long as you are considering the same soil sample with same void ratio, same constitutions and same say your structural behavior and all those things will be remaining same. So, this permeability will be used for rest of the problem. Now, in the second part, so it is asked that the height of water level in the standpipe after another 20 minutes. That means, you have waited till 12 minutes. So, head was falling from 60 centimeter to 45 centimeter, and then we are considering another 20 minutes, and then we want to find out that how much will be the head. Okay. So, in the standpipe. So, let small h be the head at the end of another 20 minutes. Okay. So, therefore, in the previous expression, now you have got the coefficient of permeability. So, that is not unknown to me. So, 3.51 10 to the power minus 5 is equal to pi by 4 into 0.75 whole square into 15. The sample is remaining same. So, the length of the sample will be 15 centimeter divided by pi by 4, 9.8 square, another 20 minutes, right. So, that means I am expressing that thing in terms of second. So, 20 into 60 log base E. Now, from this is 45 is your initial head. Now, because you have allowed the water to fall from 60 to 45 centimeter, and then you are starting the experiment for another 20 minutes. So, that means your initial head will be your 45. So, 45 will be coming as H1, and this is your final head after 20 minutes, okay, for another 20 minutes. So, from this if you solve, you will be getting H equal to 27.86 centimeter. Okay. So, this is the final head after another 20 minutes of the test. Now, we will go to the third part. The third part says it is asking that the time required for the water level to drop to 10 centimeter. That means, you are say suppose you are starting from 45 say centimeter, that is your initial height say in the standpipe. Now, you are allowing the water level to fall in the standpipe to fall from 45 centimeter to some I mean head say that is given as 10 centimeter. Now, how much time is required for that? So, let us solve that problem. So, let T be the time required for the head to drop from 45 centimeter, that is say initial height. I mean it will not be changing, say if you start from say 60 centimeter or if you start from 45 centimeter. So, I mean accordingly your time will be adjusted, because your coefficient of permeability is remaining unchanged. So, to drop from 45 centimeter to 10 centimeter. Okay. So, we can write T equal to AL by AK into ln H1 by H2. So, this is your expression. Okay. So, here you know small a, you know capital L, that is 15 centimeter, you know capital A, that is pi by 4 into 9.8 square, and you know K, that is 3.51 into 10 to the power minus 5 into ln 45, that is your H1, and H2 is 10. So, you are allowing to fall the water, okay, up to 10 centimeter. So, that is coming 3764.65 second, which is nothing but 1 hour 2 minutes 45 seconds, right. So, I hope that you have understood the problem. So, it is, this problem is good for some warm up kind of thing to understand the behavior of soil under permeability topic, our permeability chapter. Okay. So, this much of time, that is 1 hour 2 minutes 45 seconds is required for the water to fall from 45 centimeter to 10 centimeter in the standpipe. Okay. Now, we will go to the next problem. Let us see what the next problem says. So, that is problem 10. The next problem says that a pumping out test was carried out in the field in order to determine the average coefficient of permeability of a 18 meter thick sand layer. Okay. The groundwater table was located at a depth of 2.2 meter below the ground level. A steady state was reached when the discharge from the well was 21.5 liter per second. At this stage, the drawdown in the test well was 2.54 meter, while the drawdowns in two observation wells situated at 8 meter and 20 meter from the test well were found to be 1.76 meter and 1.27 meter respectively. So, determine the following. First one is coefficient of permeability of the sand layer, and the second one is effective size of the sand. Effective size means D10. You know from the earlier discussion that effective size is nothing but your D10. Okay. Now, let us solve this problem. Okay. So, the problem 10, the first part, basically we are going to calculate the coefficient of permeability. Now, we have from our theory whatever we have covered, right. So, K was given, could you remember that? So, Q into ln R1 by R2 divided by pi into H1 square by H2 square. So, that was the expression we derived for the permeability test in the field by pumping from wells. So, if you remember, then R1 is the, I mean if you recall or if you refer the previous lecture, you will see that R1 was the radial distance of the observation well 1, okay, from the test well. Similarly, R2 was the radial distance of the observation well 2 from the test well, whereas observation well 1 was the furthest observation well, and observation well 2 was the nearest observation well as with respect to the test well. Now, whereas H1 and H2 are the heads, water head available at observation well 1 and observation well 2 respectively. So, now we need to find out the different parameters or the magnitude of the different parameters to obtain this coefficient of permeability. So, first we need to find out Q, that is the rate of discharge, okay, rate of flow. So, that is given in the problem. If you recall the problem, that is given as 21.5 liter per second, which comes around 21.5 into 10 to the power 3 by 10 to the power 6 meter cube per second. Okay. Now, R1 is how much? That is the radial distance of the observation well 1 from the test well, that is the farthest well. So, that is given as 20 meter, whereas R2 is given as 8 meter. Okay. Now, the height of water table above the base of the well is equal to how much? Now, what was the depth of the well? The depth of the well was the thickness of the sand layer, that is 18 meter. Now, what is the depth of water table below the ground level? That is 2.2 meter. That means, the water table is situated at 2.2 meter below the ground level. So, that means, in the well, whatever observation well or the test well, whatever you consider before pumping out, right. So, the water table above the base of the well will be the total depth of the well, that is 18 meter, minus the depth of the water table below the ground level. So, that will give you the water table available at the wells. Okay. So, that is given as 18 minus 2.2 meter, that comes as 15.8 meter. Okay, fine. So, that is the water table available at different wells before the pumping. Okay. Now, you started pumping and you consider the steady state is reached. Okay. So, the drawdown after pumping out the water, drawdown in the observation wells, that is given as S1 is 1.27. If you refer the problem, you will get these values, and S2 is given as 1.76 meter, right. Therefore, the height of water in the observation wells is given as H1. Now, in this equation we are going to find out this H1 and H2. So, H1 is equal to H, that is the total water level or the water height, okay, available in the observation well 1, okay, before pumping is started. So, H is the height available. Now, you have started the pumping. So, you have got the drawdown, and that is S1. So, after when the steady state is reached, so this is the water height, okay, water table level in the observation well 1. So, that comes as 15.58 minus 1.27, that comes as 14.53 meter. Similarly, we can find out H2, that is H minus S2, which is equal to 15.8 minus 1.76 is equal to 14.04 meter. Okay. Now, we will put all these things in the previous expression of coefficient of permeability. So, K can be obtained as 21.5 into 10 to the power 3 ln 20 by 8 divided by 10 to the power 6. So, this is your total rate of flow into pi into 14.53 14.53 whole square minus 14.04 whole square. So, that is H 1 and H 2 as obtained earlier. So, this gives me 4.479 into 10 to the power minus 4 meter per second, which is nothing but 4.479 into 10 to the power minus 2 centimeter per second. So, from your field experiment through the wells, you have got the permeability available in the field as 4.479 into 10 to the power minus 2 centimeter per second. I hope that you have understood how we can proceed this kind of problem. Now, going to the second part, that is, you need to find out the effective size, right. So, in the second part of the problem, the effective size can be determined from some empirical relation, whatever we have covered, that is Hazen's formula. Okay. So, Hazen's formula was given as k into C some constant into d10 square, where k is in centimeter per second and d10 will be available or will be calculated in millimeter. So, your d10 is nothing but root over k by C. So, let us assume, if you recall, C was varying from 1 to 1.5. So, we are considering C as 1, okay, for example. So, assume C as 1. So, your d10 will be 4.479 into 10 to the power minus 2, that should be expressed in centimeter per second divided by 1, which comes around 0.212 millimeter. So, this is your effective size of the soil sample or the soil in the field. So, you have got these informations basically. Now, you can collect some soil sample from the deposit and you can find out the grain size distribution, and from there you can verify that what is the d10 value and how much it is coming, okay, fine. So, thank you very much. So, I will stop here today. In the next class, we will be taking one more example and then we will be starting some new chapter, that is seepage in soil. Thank you.